Okay, so we've talked a ton about sine and cosine now, but there is something that's been absent from our discussion so far that's part of the normal SOHCAHTOA saying, and that is tangent. So let's talk about what tangent is in terms of SOHCAHTOA, in terms of sine and cosine, and in terms of the unit circle. So the SOHCAHTOA definition tells us that the tangent of an angle is the opposite side of that angle over the hypotenuse. On the unit circle, if we have this angle, the opposite side is y, and adjacent side. Opposite over adjacent. Been talking about sine for so long. Okay. Opposite over adjacent. The unit circle, the opposite side is y, the adjacent side is x. So that opposite over adjacent comes out to be the same thing as y over x. But we also know that y is the sine of theta and x is the cosine of theta, so that means the tangent is also sine over cosine. So any of these definitions, opposite over adjacent, y over x, sine over cosine, will work. You probably remember from before that when we started with just these SOHCAHTOA definitions, that really only let us look at angles between 0 and 90 degrees or 0 and pi over 2 radians. And then we kind of expanded those definitions to cover the whole unit circle. Tangent's going to work the exact same way, where we can use this opposite over adjacent definition to understand what's going on with it, and then we can still extend that definition to include x and y values in all four quadrants along the entire unit circle. So let's talk about why this is called the tangent. This blue triangle in here is a right triangle, because this is a right angle, which means that it follows the Pythagorean theorem, and it means that the ratios of its sides are the trig functions like sine, cosine, and tangent. So the tangent of this angle is the opposite over the adjacent, y over x. But we can also draw a similar right triangle. So if I, instead of making this triangle by going straight down from this point, I take this point on the unit circle and I draw a line that is tangent to the unit circle, meaning it touches it just at that one point. And I draw that line down to the x-axis. This also makes a right triangle. You might remember from geometry that this line segment is a radius of the circle. This is a tangent segment. These two are always perpendicular to each other. So this line and this line also form a right angle. So when we think about this triangle in here, we can also think about this slightly bigger triangle. And these two triangles have two of the same angles. This angle is the same because it's in the same place. And this is a right angle for this triangle that includes this red side that I've labeled T. And this is a right angle for this triangle. So if we think about this triangle that I'm going to shade in like this, this bigger triangle, and we want to think about the tangent of theta, we can still ask, what's the ratio of the opposite to the adjacent? And that ratio should be the same whether we're talking about this bigger triangle or the little one that we started with. That ratio is y over x, but here in this new triangle, the opposite is t, and the adjacent side is this one, which isn't labeled, but because it's the radius of the unit circle, we know it has a length of 1. So the tangent of theta should be the ratio y over x. It should also be the ratio of this tangent line segment over 1, which is just equal to this length. So now we kind of have a visualization of what the tangent is based on the angle of the unit circle, but doesn't require us to divide two things. The sine is this line. This line segment is the cosine. And this line segment, where we take a point on the unit circle and we draw a tangent line down to the x-axis, the length of this line will be the tangent. Let's see what happens when we take an angle that is close to 90 degrees. So I'm going to draw a new angle in here. So this angle is getting pretty close to 90 degrees. And it's easy to find the sine and cosine. The sine, it's almost to the top. This y coordinate is going to be almost 1. And the cosine of this angle is this little length here, which is going to be a small number close to 0. So the tangent is the y over x, the sine over the cosine. We're taking a number close to 1, and we're dividing it by a small number that's close to 0. So when we divide these two things, 1 or close to 1 divided by something that's a small number, we tend to get a big number. Dividing by a number that's close to 0 gives you a really big number. Let's visualize what this actually looks like on the tangent line. So if I try to draw a line that is tangent to the unit circle at this point and connect it down to the x-axis, actually I even ran out of space on my ruler, it's going to take me like across the entire page. The x-axis is this line on the graph paper, so all the way over here, the tangent of this angle is now the length of this line. The tangent can be a big number. So this is much longer than any of the lengths of the unit circle itself, and if we had gotten even closer to 90 degrees, it would be even longer. So even though the sine and cosine are always between -1 and 1, tangent can be a big number. You can think about this because you're dividing by a small number, or in terms of this picture, when you draw a line that's tangent to the unit circle down to the x-axis, that line can be pretty long if your angle is close to the top or bottom of the unit circle. Okay. So we talked about it between 0 and pi over 2 degrees. Let's try to actually plot some of those points on the graph. So the tangent of 0 is going to be the sine of 0 over the cosine of 0. Actually, let's make a little chart. Sine, cosine, tangent. So we have 0, let's do pi over 6, pi over 4, pi over 3, and pi over 2. Okay. We should be pretty confident on the sine and cosine at this point. Sine of 0 is 0. Sine of pi over 6 is 1/2. Sine of pi over 4 is root 2 over 2, which is about 0.7. Sine of pi over 3, root 3 over 2. Sine of pi over 2 is 1. Cosine goes the other direction. 1, root 3 over 2, root 2 over 2, 1/2, 0. So the tangent of each of these is going to be this number divided by this number. 0 divided by 1 is 0. So the tangent of 0 is 0. 1/2 divided by the square root of 3 over 2 comes out to be 1 over the square root of 3, or about 0.58. These two numbers are the same, so when we divide them, we will get 1. These two numbers, square root of 3 over 2 divided by 1/2, it comes out to be the square root of 3, which is about 1.73. And then 1 over 0 is undefined. If you type it in the calculator, you'll get an error. You cannot divide by 0. So if I plot these in, pi over 6 will be right about here. Pi over 4 is going to be up at 1. Pi over 3 is 1.73. So right about here. And then pi over 2, I don't have a way to write in because it doesn't have, it's undefined. So far, I see this shape that almost looks like graphing the square root of x. It's got this sort of curve upward. But before we connect those together, let's do a little bit more investigating. If we go around the unit circle, we can think about angles over here, and over here. To get to angles over here, we can either keep going, or we could use negative angles between 0 and negative pi over 2. And on all these angles, the sine will be the negative of what it was, the cosine will be the same as what it was. So the tangent of negative pi over 6 would be negative 1/2 divided by this, and I would get negative 0.58. The tangent of negative pi over 4 would be down here. This would be negative, this would still be positive. When I divide them, I would get negative 1. Oops, I'm in the wrong spot. Here we go. This is not correct. This is negative pi over 4. The tangent of negative pi over 3 would be negative 0.173, or 1.73, which is right about here. And the tangent of negative pi over 2 would again be undefined. So if we connect all these together, we see that we get this kind of S shape almost that goes up as we move from left to right. It's really steep on the two ends, and it's not as steep in the middle, but it does not flatten out the way that the square root of x does. Okay. So this is kind of what the graph of tangent looks like. We can't do pi over 2, but we could actually keep going. And just like over here, where the x-coordinates were all positive, the y-coordinates were all negative, in this quadrant, the x-coordinates are negative, the y-coordinates are positive. We're going to get negative values of tangent again. So it turns out that we are going to get this negative 1.73 again, negative 1, negative 0.58, and then we would get 0 again at pi. And if we were to go over here, between negative pi and negative pi over 2, that's this quadrant, both the x and the y coordinates are negative, which means that when we divide them, we get a positive result. Here, here, here we go. Okay. Cool. So the tangent graph actually has these kind of breaks in it. And these breaks happen at negative pi over 2, at pi over 2, and at any other angle where we are close to either the top or the bottom of the circle, because that tangent line is going to be super long to get to the x-axis. And if we draw a tangent line exactly from this point, it would just be parallel to the x-axis. It would never touch it. So we can't really draw a tangent line down to the x-axis. That's one way to visualize it. So if we go around the circle with tangent, instead of kind of smoothly moving up and down the way that we do with the x and y coordinates with sine and cosine, instead we see this weird pattern where as we move, this line is getting longer, 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 disappears completely, and then kind of reappears on the other side. And this represents this break in the graph where our values are getting higher and higher, they disappear, and then on the other side they become negative. So here, y over x is positive. Here, y over x is negative. Here, y over x is positive again because they're both negative. And here, y over x is negative. All right. Cool. We will get more practice with looking at this graph and trying to understand it better as we go. But this sort of S shape is characteristic of tangent. And if we were to zoom out, we would see this S shape with a break repeating in the same way that we saw the moving up and down repeating with sine and cosine. All right, thanks for tuning in. Let me know if you have any questions. I'll talk to you again soon.